Good morning, everyone. Today we're going to look at Unit 3, Lesson 6, Factoring Difference of Squares. So it's a short note today, and we basically have a special case of factoring. We're going to take a look at expanding and simplifying a couple of binomial multiplication examples and talk about what do we notice about these specific binomials. So we have x plus 3, x minus 3. If we are going to expand and simplify, we would use FOIL. Remember, we would do our first terms, outside terms, inside terms, and last terms. Okay, so we're going to have x squared. Our outside terms, we have negative 3 times x. Our inside terms would be positive 3 times x. And our last terms, we have positive 3 times negative 3 is a negative 9. Okay, so when we combine our like terms, in the middle here, negative 3x plus 3x equals 0x minus 9. And we don't need to write that plus 0x. So we end up with just x squared minus 9. Okay, we're going to look at the next one. Then we're going to do the same thing. Let's go ahead and FOIL that. Okay, we have 2x minus 5 times 2x plus 5. So we'll multiply our first terms, outside, inside, and last. Okay, so our first terms, we have 2x times 2x, would be 4x squared. Our outside terms, we have 2x times a positive 5. And then we have negative 5 times 2x, so it's going to be a minus 10x. And then our last terms, we have negative 5 times positive 5, so we're going to have a minus 25. Same idea here, combine our like terms. So 10x minus 10x is going to be 0x. And we're left with 4x squared minus 25. So hopefully what you notice here is that in both cases, our middle term zeroes out. Okay, you can see that happened over here too. And so if you look at these two binomial multiplication examples, what is it about them that you think made them both zero out? We have the same numbers in our brackets. The only difference is that one of them is plus and one of them is minus. So it looks like when we have those same binomials, let's just make a note here, we have our same binomials with one with a plus and one with a minus. By doing that, our middle term essentially drops out because we're minusing some term and then we're adding that same term to the equation. So what happens is it makes that middle term go to 0. So this is a very special case of factoring, and it's called the difference of squares factoring. So here's some of the things that must be true about the algebraic expression for it to be a difference of squares. You must only have two terms. Okay. You must be able to square root both terms, and you must have a minus sign between the terms. So if you look at our examples above, when we expanded and simplified, so once we were in expanded form, both of our terms were what we call perfect squares, meaning we could take the square root of them and we'd have a whole number. So 4 is a perfect square, 25 is a perfect square. If we look at our first example, we have 1x squared minus 9. That also brings me to x squared is a perfect square. If we take the square root of something being squared, it just gives us the base there. So the square root of x squared would be x, and the square root of 9 would be 3. So let's take a look at how we go about factoring them, okay? So we have x squared minus 16. So we have one of two options. We can still do SPF even though this looks a little bit different. So if we wanted to write it in expanded form, like it would have been seen before the middle term dropped away, it really would have looked something like this, right? We're used to seeing ax plus bx, ax squared plus bx plus c. Okay, in this case, if I wanted to rewrite it like that, I would just put it as a 0x in the middle because it wasn't represented in the original equation. So if we set that up using SPF, we would need two numbers that add to 0 and multiply to 16. Okay, well those two numbers would be a +4 and a -4, right? Or we could simply take the square root of both terms. Okay, so we had x plus 4 and we have x minus 4 with the factors we found here. If we were to take the square root of both terms, right, the square root of x squared is x, the square root of 16 is 4. Okay, so we take our x, it goes in our bracket here, and it goes in our bracket here, like always. And we take the square root of 16, it goes here, and it goes here. And then we just make one positive and one negative. Okay, let's take a look at another example where we don't have so many arrows drawn. So if we have 9a squared minus 4, and we just take the square root of 9a squared, and we take the square root of 4. The square root of 9a squared is going to be 3a, and the square root of 4 is going to be 2. So we set up our two brackets, so we should end up with those two binomials. We'll have 3a and 2 in one bracket, 3a and 2 in the other bracket. One is plus, one is minus, and you're done. Okay, if we look at C, similar situation, but our variable and our constant are flipped. So we have to make sure we write them in that order as well when we factor. So if we knew the square root of 100 and the square root of x squared, the square root of 100 is 10, and x squared is x. Okay, so if we put them in brackets, we'll have a 10 and we'll have an x, making sure we write them in the order in which they were originally presented. 10x, we make one positive, and we make one negative. Okay, go ahead and pause the video and try the next one on your own. So there's the solution to the next one. If you were to square root 64 and you were to square root 49, that's the factors you would get. And we'll take a look at E and F together. If we were to look at, this time we have x to the power of 4. So that's a little bit different. We've only been looking at x to the power of 3. But when we see a number in the exponent like that, we think of it just like we think of a base. If we were to take the square root of it, what is the square root of 4? So if we were to take the square root of x to the power of 4, it would be x, and then square rooting 4 would just be 2. So the square root of x4 would be x squared, and then the square root of 81 would be 9. So again, we have x squared plus 9, and we have x squared minus 9. So when we look at them this time, now we ended up with two binomials, each of which has a squared in it. So we should think to ourselves, can this be factored further? And remember, to be a difference of squares, you need two terms. So I have two terms here, and I have two terms here. The second qualification is you must be able to square root both terms. Well, I can square root an x squared, and I can square root a 9. So again, I can do that to both of these as well. And then our third kind of qualification is that there has to be a minus sign between. So only our second bracket has a minus sign, so that's telling me I should be able to factor that second bracket some more. So we have another difference of squares. to factor. So I can't factor this x squared plus 9 anymore because there's no minus there to do that. But I could factor this one further, right? X squared with the square root is x, and a square root of 9 is 3. So that would factor to x plus 3, x minus 3. Okay, last one. This last example, it doesn't look like a difference of squares, because is 7 a perfect square? Is 28 a perfect square? This brings me to a point too. We should know our perfect squares or be able to look at them and say, I know I can take the square root of my numbers, or of that number. So sometimes it's helpful to have a list of perfect squares. And if you just see it in your note, you might get used to those numbers are perfect squares. So when we think of perfect squares, we have to think of numbers that result from a certain number being multiplied by itself. For example, 1 times 1 is 1. So 1's a perfect square. 2 times 2 is 4. 4 is a perfect square. Okay, if you continued this list, right, how far could you get? I mean, you could go on forever, but the perfect squares you should know. So 5 times 5 would be 25, and then we'd have 36, 49, 64, 81, 100. That's 11 times 11 is 121, and 12 times 12 is 144. I would say you should know that all those numbers are perfect squares generally. So if we looked at our last example here, we have 7y to the power of 4 minus 28. If I look at my list of perfect squares, I don't see either of those numbers on there. So we have to think about how could we factor this. And we should really always think about common factoring first. So let's try to common factor first and see if that presents itself in some other way. So we're going to common factor first. So I'm going to pull out a 7 because I can see 7's a common factor of 7y4 and 28. So when I pull out a 7, I'll be left with y4 minus 4. Okay, now is y to the power of 4 a perfect square? Yep. And is 4 a perfect square? It is. So now I could factor using a difference of squares. So we're going to have y squared, and we're going to have 2. So we'll leave our 7 outside. We can't lose that common factor. And then we'll have y squared plus 2, and we'll have y squared minus 2. Okay. Now we still have that y, and we have it to the power of 2. So we have to look at, could we factor those further? But again, they would have to be perfect squares for us to factor them. And in this case, we don't have a binomial that has both perfect squares. All right, that's it for your note for today.